so today we're going to look at AC waveforms. So an AC waveform looks something like this, with this value here being the voltage peak to peak from the two crests of the wave. In a capacitor, this value lags by 90 degrees, and so therefore looks something like this. And in an inductor, it leads by 90 degrees and looks something like this. To calculate the RMS value for the wave, we use the equation V RMS equals voltage peak to peak divided by √2. Alright, so with our circuits, we have series and parallel configuration for inductors, and when you add inductors, you add them like you add resistors, add their values. So you add the two in parallel with 1 over L1 plus 1 over L2, etc. And in series, you then just add them normally, so L1 plus L2, and that would lead to the final equation for this circuit for inductors to be LT equals 1 over L1 plus 1 over L2 to the -1 plus L3. So we're adding these two like this, and then adding the value that we receive to this one normally. For capacitors, we have, it adds the other way. So these two capacitance values add like normally, so C1 plus C2 plus C3, and then the value that's received there, we then add to this last value via 1 over the value. So 1 over C1 plus 1 over C2 plus 1 over C3 to give us this final equation down here. Alright, so finally we have the impedance in an AC circuit. So impedance is essentially the resistance to AC current in an AC circuit, obviously. So the total impedance equals the value of any resistors plus J, which is an imaginary number operator, plus omega, which is equal to 2 pi f. So f is the frequency of the AC generator. So the omega L is the inductor section, and the 1 on omega C is the capacitor section. So if you want to equate inductor and capacitors in terms of impedance, you would use this formula.